able to get the, has everybody got the OneNote link?
Yeah.
Anybody not get it? Okay. Has everybody seen the homework that's posted? All right. You didn't see the homework? Do you have the OneNote link?
Yes.
Isn't it on OneNote? But you didn't see it there?
The OneNote that I got just has the notes. It didn't have a homework section.
Yes, sir. What's that?
Mine's the exact same.
How many aren't able to view the homework there? One, and you two? How many can view it? All right, the homework should be very clear. Could you see me after class and I'll try to figure out what's wrong? This should be a seamless thing. If you press that link, you should be able to go to it and view it. And I assign the problems by number, then I give you the solutions too, I believe, right? All right. Now, most people at this point, they have access to solutions all over the web and stuff. It's not even advantageous to think that students don't have access to the solutions for any problems that are in the back of the book. Now, if I create my own, it's a little different, but I want to make sure that I give that to you. I'm trying to help you as much as I can. So are there any questions about the homework? Yes, sir.
Did you just say that you posted solutions to homework?
How many saw the solutions on there? Aren't there? Okay, I will post the solutions. If they're not, that's on me. And I'll be honest with you. How many have access to the solutions? One? Only
I think the solutions are in the back of the book for the odd numbers.
Well, the PDF solutions, I'll tell you, I come in sometimes, the kids, even before I post them, they have their solution there. I'm just telling you it's out there. All right. I make absolutely sure I post it. Would you do me a favor? I mean, these aren't hard problems, but somebody send me an email. I'm very good, especially just put in the subject, solutions for EMEG2 or something like that, because I get a cajillion emails and it's really hard to wade through so many silly things like, you're invited to this function in Birmingham. All right. Anyway, next. So, did you have a question about the problem? Or not?
I know. Like, I'll just ask it if you do post a solution.
I will.
Okay.
And that's on me. These problems I gave you are very simple. Does anybody have any questions about the problems I gave you? Usually I get several, but I'm surprised I did. How many did them? Just be honest. I'm not going to come at you hard. Couple? You didn't do them? You did. You did them. So, I'm glad I'm not a surgeon. The word "whoops" is what you don't want to hear from a surgeon. Anyway, anybody have any questions that did the homework? Do you agree they're easy? It's whenever I get this, let's not go easy. Let's say they were challenging. Okay, are you okay with that? All right, so based on that, what they're trying to do is just bring you up to speed so you have a feel for this stuff. Now, I warn you about one thing, don't get behind. Don't think that, you've got it and you can handle it, because you'll get creamed in here. There's no formula cards. Everything builds. I don't think I said this clearly enough last time. Everything we do in the final phases of this course is premised on an understanding of the early part. Y'all follow me on this? So if you don't know Maxwell's equations and how to deal with it and the solution to it, by the time you get to the last part, you'll be completely lost. It's like not knowing where the wrench is and talk about auto mechanics to somebody when you're doing like a timing thing, all right? So you have to understand all the basics. Anyway, where I left off last time was with Maxwell's equations and getting a single equation with a single unknown, and then finding out the propagation, really the properties of propagation. So we're going to be talking about propagating electromagnetic fields. And do you all remember I said we're not talking about being real close to the source of the electromagnetic field. Remember, we're a long way away. Y'all follow me on that? Like a long way from where the puddle fell, the waves become plane. That's what we're doing here. So we started, and I'll just take you through this kind of quickly. I had the curl of H, and I already went to the phase of the domain, so that was equal to sigma plus j omega epsilon times E, right? Do you remember the name of that law? Anyone? Begins with an A. Ampere's law, right? That's Ampere's law. And then we had the curl of E is equal to minus j omega mu times h. Now, I made this, what's the name of this law? Has to do with the guy with the first name is mine. Michael Faraday's law of induction. Or this is Faraday's law. Anyway, I've already made the substitutions that B is equal to mu h, right? D is equal to epsilon E, right? And then we have J equals sigma E. We did all this stuff last class, I'm just reminding you. I also said divergence of D is equal to the volume charge density, or the divergence of E is equal to rho V over epsilon. I'm just putting this up here to remind you. That's what we used to get to that point with the basic Maxwell's equations. Now we got one equation with one unknown. Do you remember how we got that? Anyone? Anyone?
Just a curl again.
Yeah, you're right. Whoever said that's right. I'm going to take another curl of this guy, and your wide angle lens sees this? Okay. All right. So I'm going to say curl of E is equal to minus J omega mu times curl of H. I don't think I did it this way last time. I'm just showing you the full-fledged version. Y'all with me? Curl on both sides. Now I did one thing, and I'm going to move over there. I get a vector identity on curl of E that you probably don't know, because you didn't have vector calculus. That requirement's not, it's, I guess that was dropped some time ago, but it's a straightforward identity. That becomes the gradient of the divergence of E minus del squared of E. You don't have to understand this proof thoroughly, but it helps. If you can see where things come from, you can always go back and figure it out. And in engineering, you have to know where things come from. That's just the way it is. That's the curl of E right here, is equal to this, is equal to minus J omega mu. And what did I do with that curl of H? Somebody? I know you said it last time. What did I replace this with? So I just have E. Right here, right? Ampere's law. Ampere's law. So I did that, and I have sigma plus J omega epsilon times E. Now that equation is a simple, well, it's a differential equation, second order spatial differential equation, because these are second order derivatives. But we got rid of the actual temporal derivatives by going to the phasor domain. And remember, you did that in circuits. That's the one thing I try to remind you of, right? In circuits, you don't do differential equation solutions. You just say, at a constant frequency, like the impedance of an inductor is J omega L, right? Y'all remember this? And you don't solve diffie cubes. Now we get to this point, and here we make some assumptions. We're talking about plane waves. And last time when I did this, I assumed that rho v equaled 0. What did that do for me, anyway? Y'all hear me okay? There's one thing it does for me really quick. What happens if rho v here is 0? What is div e, anyone? 0. If div e is 0, the gradient of 0 is? 0. That's the idea. So that goes away. Now, I'm going to start doing what, as engineers, you should get in the habit of doing. Whenever you got a whole bunch of constants hanging out that you're going to keep repeating, create a single variable to indicate what that constant is. Here we use gamma traditionally. And gamma is going to have a real and an imaginary part. And that's equal to actually the square root of J omega mu times sigma plus J omega epsilon. All right, now this gamma is something you're gonna find out. It's really the propagation constant. It's equal to alpha, which is an attenuation constant. It tells you how fast things decay. The bigger that number, the faster that wave will decay in an environment it's propagating through. And beta is called the wave number. That's how many radians per meter the wave is. If you think about that, remember, this is at a constant frequency. So if we just look spatially, froze time, we'd see a wave that does this, right? We get wavelength from the wave number, because if we think about it, beta is going to be in an argument in a sense inside a cosine. We'll see that. Beta times the actual wavelength has to be 2 pi. And I'll get to that, but I'm just telling you some things to keep in the back of your mind. So then I take this equation, I take this, minus del squared of E to the other side, and I replace that with gamma squared, because if this is gamma, you square it and get that term. And you end up with this. Right here. Do y'all remember me doing that last time? Or kind of sort of, right? This is important. Now that del squared operator I mentioned is an actual vector Laplacian. It's not a scalar. E is a vector, and in general, if you're doing spherical or cylindrical coordinates, this del squared operator doesn't break down like the scalar these scalar operators he has in the back of the book. So just be on guard, all right, in case later on you see that. But what we do now is make some assumptions. We assume we're a long way from the source, and we're going to assume this. I'll just tell you what this comes down to. This del squared operator, if we assume we have an E field only in the x direction, propagating in the z direction. So you might say the propagation is going to be in the z direction, and the polarization of E is going to be in the x direction. That double derivative will become the second derivative of EX with respect to z squared. Now remember, this del squared derivative would have second derivatives of E with respect to y and z, but they're both zero, because I made the point that that electric field is only going to have a variation in the z direction in magnitude. Do y'all remember me talking about that? So I have that minus gamma squared of E, and this is going to be an x component, equals 0. Now that's just substituting for that and making it real simple. We got rid of a lot of variations. This is a plane wave. It's propagating in the z direction. It's a long way from the source, and it's only got a polarization in the x. It could have a polarization in the y as well. A lot of things can happen, but we've tried to simplify this in a way that's not too simple. This is a very meaningful example, and it's applicable to things. All right, so this is real. This is something you can use. Get down here in the solutions to this. We could do Laplace transforms. We could do just better. If you look at this, this is a standard second order homogeneous differential equation. You were taught the solutions will be in the form of what? I'm not going to, it's Whitworth does this in his book, but you remember the solutions would be in the form of some scalar variable, right? E to the minus lambda z. Y'all remember that? And you just do the derivatives and set it equal to 0 and solve for lambda. That's the way you did it back in the day when you had diff EQ. When you do that, these are the solutions, and I'll put them right under here. You find out that the E field itself will be some EX0 plus, make sure you put that plus there, times E to the minus gamma z, plus EX0 minus E to the minus gamma z. And now I tell students at this point, make sure you put a little arrow here. This portion of the solution is propagating in the plus z direction, and this portion is going in the minus z direction. Y'all with me?
Dr. Baginski, yesterday you had positive gamma z on the last term.
Yeah, I'm sorry. It is positive gamma z. I'm so glad. Thank you. Thank you. It is positive gamma z. Yeah, my bad. And we would find that out the hard way, but it's absolutely right. And if you check, you take either of these solutions, because solutions, if you have a solutions for one and another solution, if you add the two together and turn the crank, it'll be the solution. If you just put this in there, it'll work. If you just put this in there, it'll work, all right? It comes to 0, guaranteed. Anyway, when I take a look at this, that is in the frequency domain. It is a phasor. There's no omega t in there, right? If we want to see the time domain form, and I know this is frequency because it's got e to the minus gamma z, and gamma's got the imaginary part. Dr. Gross would tell you to put a little tilde over that. I'm not going to hold you to that. All right, but how many have had Dr. Gross? Well, then you know. He's a stickler for detail. It's probably good, but there's certain things that are just obvious, and I don't worry about that. Anyway, when you have that, that's in the phasor domain. To go to the time domain, the E field here, it would be a function of zt, would be the real part of e to the j omega t times the phasor, which is this, and it would be ex0 plus e to the minus gamma z. And actually what I'm going to do here, I'm going to replace gamma with alpha plus j omega. So e to the minus alpha z e to the minus j beta z plus ex0 minus e to the gamma z times e to the j beta z. And the only thing I've done there is I've gone ahead and replaced gamma with alpha plus j beta, and then to get the time domain form, I have to multiply it by e to the j omega t. Do y'all follow me on this, class? It's a bit of a, I know it kind of is irritating to write all that, but I'm trying to be clear. Y'all with me? Okay. Now, what do I do here when I take a look at the real part? Well, you see that, first of all, ex0 is going to be a scalar. It's nothing but real. Next, e to the minus alpha z, that's also strict real. It's like e to the minus 5, e to the minus 10. It's a real number. There's no imaginary component. Here's where the imaginary component is. E to the minus j beta z. Does everybody see that? Now when I multiply that by e to the plus j omega t, I get e to the j omega t minus beta z, right? Quantity j times quantity omega t minus beta z, right? Do you remember what I told you what the real part amounts to, really? I said I used Euler's identity, and you'll use this all the time. That's the cosine of theta, whatever theta is, plus j sine of theta, right? When you take the real part, you just take the cosine of whatever that exponential argument is. Are you with me on this, class? How many see this and can follow my train of thought? You okay with that? In the back here? Okay. So when I do this in the real part, the e to the j omega t times e to the minus j beta z become e to the j theta, and theta is omega t minus beta z, and it comes down to this. My E field as a function of z and t becomes some ex0 plus times e to the minus alpha z times cosine of omega t minus beta z. Then it's plus ex0 minus e to the plus alpha z times cosine of omega t plus beta z. And here, if you want to, you can put this. This is a wave traveling in the plus z direction, and this is a wave traveling in the minus z direction. But it's the time domain form, and I like to do this one time to make sure everybody sees where this comes from. Y'all with me? Now, if it's propagating in a material that doesn't have any loss, something where there is no currents induced, like a vacuum, then alpha will be 0. Do y'all follow me? And if there's only a positive going wave, this part's gone, the last part. I'm just making note of this so it's in the back of your mind. Now, you've seen these kind of equations in physics before. You've seen it in mathematics. You probably saw something like this, definitely in your kinematics classes, but do y'all remember the problem back in physics? You take a rope and whip it right, and you get waves, right? Well, this is the same type of solution, only now our waves are not, you might say, linked to the displacement of a string or a rope, but here the waves have to do with the magnitude of a invisible quantity we call the E field that can be measured in a certain direction. So the E field is perpendicular to the direction of propagation, and that's true generally for waves. Displacement, in our case the E field, is perpendicular to the direction the wave's flowing or traveling. You with me? All right. Now next, we need to talk about some specific quantities and specific features of this. And this is real important. So what I'm going to do to make things simple, I'm only going to worry about positive Z waves for now. All right? And when I do that, I find I have E will be equal to some EX0 plus. I can put the e to the minus alpha z down, but here it will not have any effect, times cosine of omega t minus beta z, right? I mean, I just took, and I got rid of the negative going waves, so I'm just taking a look at something that's propagating in a positive direction. Now, these are things you've had before. Sometimes, though, they're not really, I'd say they're not real apparent until it's brought out. So when I take a look at this, if I just took a snapshot in time of this waveform, right, it would look like this is E field here in this direction versus Z. It would look like this. Do y'all follow me? It'd basically be like that, right? I'm just take a snapshot t equals 0, right? Plot the cosine of minus beta z. It's the same thing as cosine of beta z because cosine is an even function. Cosine of x is equal to cosine of minus x. It basically would look something like that. Do y'all agree with this? Now, if I take a look at this, there's a few things I'd like to know. If I'm on the crest of this wave, how fast is it flowing? That's the first thing. That's called the phase velocity. Phase has to do, when you talk about phase velocity, is if you take a point on a wave and you track how fast, and I'm talking about a phase point, like the crest, the peak of the wave, how fast is that moving? That is the phase velocity. Are you with me on this, class? It's real important we have an appreciation for what phase velocity is. Now, phase velocity here has to do with how fast a point of constant phase is moving. You see, the phase is this argument, right? That right here is the phase of the wave, isn't it, class? The omega t minus beta z, that is an angle, right? In radians, typically, right? If we take a look at this, I'm gonna get yelled at here.
That's as far as you can go?
Okay.
You're there?
I'm gonna go back over here then.
All right.
And if anybody can't see or read my writing, please let me know. All right, back to that. Now we have E right here is equal to some EX0 plus e to the minus alpha z cosine of omega t minus beta z. I know it's in the AX direction, I don't have to write that again. But now I call the phase theta omega t minus beta z. And I want to see how fast that crest moves. Now this is the value, what? Of the angle. Like at a peak here, it would be angle of 0. Theta is 0, right? Here, it would be what? Well, for cosine, what happens? It's a maximum when? Well, it's a maximum at 0, a maximum at pi, an absolute maximum. It's actually minus 1, right? But at pi, the magnitude would be 1. At 2 pi, right? Or at n pi would have relative magnitude maximums, correct, class? So if I'm over here at pi or whatever, and I want to see how fast it goes, what I'm really going to do is take a derivative of the phase. It doesn't matter what I set this equal to. It can be k. It doesn't matter. Now I take a derivative of that phase with respect to t and set it equal to 0, and I have what? Omega equals minus beta dz dt. What that's doing, this says how fast is the point where there is no phase change moving. Do y'all follow me? If the time derivative of the phase is 0, it's not changing phase. So you're literally riding the crest of the wave and figuring out how fast that moves. Do y'all follow me? All right, dz dt we call the phase velocity. So we have omega minus beta times phase velocity. Think about it, dz dt is a rate of motion, right? Remember in physics? Dx dt was velocity. dz dt is velocity in the z direction, and now we find out that the phase velocity is simply omega over beta. That's always true. How many remember that? All right, good. I'm glad, because believe it or not, a lot of people don't. So that's just basic stuff. Now the next thing we have to do when we do this is we want to figure out the wavelength. Wavelength becomes important. And this is for a general wave, not for free space or losses. So when we talk about wavelength, that's phase velocity. The symbol we use for wavelength is lambda. And the units are gonna be meters, fault units. So, when we take a look at wavelength, what we do is go back to the equation. This is the way I do it. If I want to figure out wavelength, what I want to do is take a picture of this at a given point in time. So I'm going to just let t equal 0. At t equals 0, then I have E is equal to some EX0 plus e to the minus alpha z times cosine of minus beta z. Do you all agree with that? Now I go a step further. I said cosine was an even function. By that I mean cosine of minus x is equal to cosine of x. That's called an odd or an even function. It doesn't matter what the sign of the argument is. It's the same value. And said another way, you can take the function, if you graphed it in the positive z direction, and just take it and flip it on the negative z direction and be identical. Now a sine wave is an odd function. If you had a sine wave going this way, you would flip and then flip again. It's two flips for an odd in order to get the waveform. So now if I say that over here, that I've got cosine of minus beta z, it's really cosine of beta z, right? Same deal? Now, how do I calculate wavelength? Well, a wavelength is really the length spatially that it takes the waveform to repeat itself. It's similar to a period in time, right? So if I'm talking about a periodic waveform, sinusoidal or cosinusoidal waveform, it's really where the wave goes through 2 pi radians of change. Y'all follow me on that? So if I set beta z equal to 2 pi, the value of z that does that would be the wavelength. So then we can say wavelength is equal to 2 pi over beta. And that is the wavelength. That's how you get wavelength. 2 pi over beta. Now the 2 pi over beta, that's it. All right, that is how you get wavelength, no matter if you're in a lossy thing or a free space or anything like that. And the way you get phase velocity is right here, omega over beta. Now there's a lot of things we can do to actually reduce the complexity of this. I'm just telling you, in free space, this stuff it basically reduces to trivial stuff. But this is the general form. This includes for a high conductivity region, everything like that. You got me on that? All right, good. Now, after that, now I'm going to go and I'm going to talk about intrinsic impedance of the region. How many have heard the term intrinsic impedance? 8 or 9. Okay, if you haven't, you're about to, and this is very important. Because this, impedance in general is a ratio of what? Voltage to current, isn't it? In your circuits courses. Here, it will be a ratio of voltage to current, but it will be the electric field ratio to the H field. So if we have one or the other, or if we have one, we can get the other if we know the characteristic impedance of the region. Now I'm going to show you how this is done. So, in general, when we think about impedance and stuff, impedance is a frequency domain constant. Y'all follow me? It assumes a steady frequency. At least for most applications, there is something called surge impedance. So back when we solved the wave equation, we found the E field itself was equal to some EX0 E. Here, I'm only going to deal with a positive going Z wave here. Just put positive Z that way. This way I make a notation so you know that. When we have this, it's times e to the minus alpha z, right? Times e to the minus j beta. Actually, tell you what, since we're in the phase domain, I'm just going to use gamma. E to the minus gamma z ax, and gamma is equal to alpha plus j beta. We've got that from the wave equation. This is only going to be the positive going solution of it. And it is for a plane wave, or a long way from the source. There's only an x variation, or an x orientation. Now, the H field itself we can get. You don't need to write this down, but just listen to me for a second. I want to make sure you at least understand what goes on. You know, when I had the two curl equations, and curl of H is equal to sigma plus j omega epsilon times E, I took another curl of that one, right? Y'all remember this? I could just assume take a curl of this one. You don't have to write this down, but if you want to, I guess you can. I was just going to fly through it. So if I take another curl of this, now I get curl of H equal to sigma plus j omega epsilon times curl of E, right? Wouldn't there be a curl of E? What could I replace curl of E with?
J omega.
Right. Minus that times j omega mu H. Now I've got a single equation for H, right? Almost, as a matter of fact, it's literally identical to the other one, except I've got H there, not E. Y'all follow me? When I come down here, I break this up, I get gradient divergence of H minus del squared of H, right there, is going to be equal to, and I'm going to just substitute in gamma right off the bat, gamma minus gamma squared here times H. Now the only thing I've done is remember that's gamma squared, right? So I stuck in gamma squared, and I got this by doing a vector identity. Now, do you remember I was talking about this last time about magnetic charges, right? Do they exist? No. Rho v, the electric charge, or rho v sub e, the electric charge density, can have a non-zero value, but magnetic charges, I'm sorry, don't exist in our macroscopic world, at least for the length of time we care about. So that means the divergence of H, or divergence of B, was zero. This goes away. And you all see how this becomes the same as the last equation that I had in E, right? Y'all see that? By the same token, I'm going to jump a step ahead. The solution for H will have the same form as the E field solution. Only the orientation will be in the y direction. I'll show you that in a second. So call that HY0 plus e to the minus gamma z ay plus HY0 negative e to the gamma z ay. My point is the H field, because literally the equation is identical in every form, is going to have the same form for the solutions. That's the only point I was getting at. That's the reason I told you you don't have to write that. All right, knowing that, now I'm going to get the intrinsic impedance. I take this, and I know that curl of E is equal to minus j omega mu times the actual H field, right? By the way, what's that guy's name? What's the law here? Anyone? Guy has same first name as me.
Faraday.
Faraday's Takashi. Yeah, I'm trying to make sure I go to a job interview and I'm touching. I don't want to have some physicist interview. What is that called? I don't know. It would look bad. Anyway, come down here. Now, I know the H field form is this, and I'm going to only talk about a positive z-going version of that. But when I take the curl of it, let me do the curl over here. Curls have different forms in cylindrical or spherical than they do in Cartesian. But the curl, and this is in the back of your book on the last, if you flip the cover on the back, you'll see these things. Curl E, you can, and this would be in Cartesian coordinates only, would be have AX, AY, AZ, and then it's going to be the partial with respect to X, partial with respect to Y, partial with respect to Z, and then EX, and EY, and EZ. That's the formal curl of E. I'm going to alter that. Y'all agree with that, by the way? Do you remember seeing this in the back cover? All right, now, I said it's only got an X component, right? These two are zero. That means these two become 0, right? And I also said that the E field itself is only a function of Z. Y'all remember that? It's only propagating the Z direction. When I look at this, it means AY DDZ of EX, right? So it's in the AY direction. It's DDZ of the X component. Now, there is also minus, technically it's X, minus what? It's going to be DDY of EX in the AZ direction. Right? But there is no variation with Y, so we don't even put that there. Do y'all follow me on this? Do y'all know what I'm doing here? This is standard determinant, right? You had linear algebra? All right. So this one goes away, and we're left with that. So I know curl of E here on this side is just equal to AY, right? And then the derivative of E with respect to Z. Here's the E field. What's the derivative with respect to Z? What happens? The minus gamma comes out front, right? So you get minus gamma right there times EX0 times E to the minus gamma Z. And then that's equal to minus J omega mu. The H field I showed you had the same form of solution, so we put HX, or HY, pardon me, 0 plus E to the minus gamma Z. What I'm doing is substituting in some of the information there and the derivative there, this. Y'all with me? Catch up, and then I'm going to just make it nice for us to solve the rest of it. Okay, what I'm going to do is get rid of things we don't. Now, does everybody see the exponential goes away to E to the minus gamma Z on both sides? Y'all see that far back? All right, so I'm going to erase. Now, after that, I'm going to erase that AY because it appears on both sides. After that, what you can see is we have the ratio of EX0 positive over HX0 positive, and that's equal to, the negative signs cancel too, I should have done that, is equal to what? It's really equal to J omega mu over gamma, isn't it? Just take a look at what I'm doing. I'm going to simplify. Y'all with me? Can you see okay? And go ahead, miss.
Is that H of Y or?
Yes. Yes, thank you. I'm sorry, I need to be more attentive to detail. Yes, you're right. I should have just forget the sub stuff and call it H0. But you're right. H is in the Y direction. Y'all with me? It's just this. Now that right there, I'm going to simplify, but that is the ratio of E to H. That is the intrinsic impedance. But before I put down a symbol for it, that's equal to J omega mu over gamma, which is square root of J omega mu times sigma plus J omega epsilon, right? Y'all see that? Right? I just substituted in for gamma, right? Y'all with me? Now, what do you see here? Well, I have J omega mu to the first power, and here I have J omega u to the 1/2 power, don't I? The square root. So what I can do is change that a little and simply say it's equal to the square root, everything under the square root of J omega mu over sigma plus J omega epsilon. And that's called the intrinsic impedance, eta. I'm going to write it over here and erase my curl. So when I come over here, now I can say that eta, and you can call it eta I if you want. This is the intrinsic impedance of a region is equal to the square root of J omega mu over sigma plus J omega epsilon. And that has a magnitude and an angle. All right? Now, I want to make something clear to you, because this is the number you're going to see all over the place. if you are in free space, call it air. Really, it should be a vacuum, but in air. That means sigma is about 0. Down here, remember, didn't I tell you about what sigma was for this like air right here we're breathing last time or not? Anybody remember? It's about 10 to the minus 14, 10 to the minus 50. Just about non-existent, all right? It's very small. So when you talk about conductivity down here, it's just about 0. Not quite, but it's almost. So in free space, sigma is 0, and then I get eta, and also I should say mu is equal to simply mu naught, and epsilon is simply epsilon naught, the relative values, epsilon relative, mu relative are 1, and you get something called eta naught, and that's the intrinsic impedance of free space, and that's equal to the square root of mu naught over epsilon naught. Now mu naught is 4 pi times 10 to the minus 7. Epsilon naught, if you want to write, is 1 over 36 pi times 10 to the minus 9. When you do the math on this, this whole thing comes down to 120 pi ohms, or about 377 ohms. And that gives you the ratio of the e to the h field for a propagating wave in free space, and it's used all the time. So if you have the E field, you have the H field just by dividing it, the E field's valued by the intrinsic impedance. You with me, everyone? That's important. Something else is important too. Now remember, I've ignored the negative traveling waves, right? I ignored that portion, and I ignored for the E field the portion going in the other direction. Y'all with me? If we would go through and do the same thing I did here for the negative traveling wave, and go up here for the intrinsic impedance, this is for a positive traveling wave. But if we did that, we'd find the ratio, write this down, of EX0 minus to HX0 will be minus that value. It'll be minus, and circle the minus sign, square root of j omega mu over sigma plus j omega epsilon, or it's minus the intrinsic impedance over here for the positive going away. Y'all follow me? The negative sign happens because if you look at this sign, it's positive gamma z here. And the other one for the E field will have a positive too. Okay, so now we got intrinsic impedance down. Now, in Dr. Wentworth's book, I almost feel like doing a prom. The next thing he talks about is, yes, sir?
On the negative side, that's HY as well.
Ah, gosh, yes. For propagating waves, let me just say this. If the wave is propagating that way, say this E field just shows you the polarization relative magnitude, the H field has to be perpendicular to it, and perpendicular to the direction of propagation. If you want to, I don't know if you've seen this yet, but if you take your right hand, and everybody assumes has one, take your index finger, that's not an assumption I make lightly now. I've learned that lesson hard. There are people that are Vietnam vets and stuff like this in Afghanistan. They don't have arms on them. They don't have hands. And that's the reason I say it. Anyway, put your finger in the direction of the E field and rotate it in the direction of the H field. Your thumb points in the direction of propagation. If you have two, you have the last value. So if I have the E field, say this way, and it's propagating that way, the H field has to be this direction. E cross H, going that way. Y'all with me? You can always get it, it's called the right-hand rule. E crossed H is the direction of propagation. It's also the power, if you literally do an E crossed H, you get the power density in the actual direction that it's flowing. But I will get that. I'll talk to you more about that later. All right, next. Okay. I'm going to show you one other thing, because some of this stuff is irritating. I know. I mean, there's a lot of stuff you got to keep in your head until you do a lot of problems, and it stays there. Next thing I want to do, I'm going to jump ahead for a second and show you how to get E from H and H from E if the wave is propagating and it's plane wave. This is a nice trick. It doesn't, because usually you have to take the curl, right? You guys like doing curls? I don't. If I don't have to do them, I don't do them, because especially in spherical coordinates and stuff, some of that gets mathematically intense. And that's where a program like Mathematica that'll do it for you symbolically is really nice. But I don't have to, I won't. So, next. If you are talking about, you have to have plane waves. It's only for plane waves. Electromagnetic plane waves. It's not for the near field when you're close to something. Right? If you have E and you want H, you can find out that H, this is in the phasor domain, is simply equal to 1 over the intrinsic impedance of that region, that's a scalar, times a unit vector in the direction of propagation, and you cross that into the E field. Now I'll get to that in a second, what AP is. And likewise, if you have the H field and you want the E field, it's minus the intrinsic impedance times vector, unit vector in direction of propagation crossed into, the H field. Okay? This eliminates the need to do a curl. Dr. Wentworth has it in his book, I don't know the page number, but it's stated explicitly on the bottom of one of his pages in this chapter. It's chapter 6. And the nice thing is, the only thing you have to know is AP. And AP is a unit vector in direction of propagation. That's all it is. Now, I got 1 minute. I'm not going to have time to go through dielectrics or good conductors. That's next on Friday. Somebody's going to ask me, are we going to have a quiz this Friday? Not this Friday. We just started. We're just coming up to speed. So we won't, but please do the homework. If I see like 20% of the class, there may be one of those pop quizzes like, what is my name? And hand it in for points. I want you here if you can be, all right? If you're sick or something, let me know. And by the way, I thank you very much for being able to post this. Did you send the link or not?
I'll put it in the OneNote. I think we had. Did we have access to type
I
on that?
think you have right access to
I think so.
OneNote.
So I'll put it on the bottom of the
Yeah, but
syllabus.
send me an email, and before you run out of here, does anybody have any questions at all? I'll give you some more homework. If you didn't do the homework,